Good morning, everybody. I'm here to talk about probability today, but I also want to point out something because the rest of the semester we're going to be talking about hypothesis testing. And this is the way we use statistics to prove scientific facts. We actually conduct a hypothesis test. So we've learned a lot about how to find the associations within the data and to present those with good visualizations and to be able to show the narratives we're finding in the data. But a hypothesis test seals the deal. The hypothesis tests will provide scientific proof. Okay, so the Python reference is important and the hypothesis test is going to become important because why? Because we provide you all the code blocks you need to run these hypothesis tests. So now I'm going to launch into Notebook 10. Which I just scrolled past, sorry, Notebook 10. And we're going to talk about probability. Why? Well, we don't have a probability course, we have a statistics course, but statistics uses probability. Okay, so let's get into this and get started. So we do want to cover enough probability that you'll understand the statistics part, although this isn't a probability course. All right, so let's run the initialization code, and let's just notice this, that scipy.stats has been imported as stats. Why do I want to highlight that? Well, because we're going to end up using this stats feature throughout the notebook and later in the course. So I just wanted to show you that we're not just importing NumPy like we did before, we're importing SciPy 2, okay? So let's initialize and talk about probability. All right, so we're gonna talk about theoretical probability first. Like, how do you calculate probability? And, what's the probability of drawing a jack from a standard deck of 52 cards? Well, there are 4 jacks out of the 52, so it's 4 over 52 or 1/13. So that's what we mean by calculating a theoretical probability. The probability of flipping a coin and getting heads is 1/2. Okay. There are some attributes or properties that probability have, and they're listed here as facts about probability. What this says is that the probabilities have to be between 0 and 1. And basically what we mean there, this is decimal form, but if we switch to percentage form, right? Something has a 0% chance of happening up to a 100% chance of happening. And the closer it is to 0, right, it's virtually impossible. Again, the computers we use and the calculators we use will often round. So sometimes we get things that are very, very close to 0, which means that it's virtually impossible. And we get something very, very close to 1, which means it's virtually guaranteed. And then this is a really helpful one, the not E. And we calculate that probability as 1 minus the probability of E. So just think of this like example 1 says here. We're looking at a coin that is weighted so that the probability of heads is 2/3. Then what's the probability of tails? And then the idea, the thing that relates it to this not E, right? E is the experiment, the probability that the experiment is conducted and something happens, all right? In this case, heads. So what is the probability of tails? The probability of tails is 1 minus the probability of heads. This is the probability of not heads, right? So you do the 1 minus 2/3, which is 1/3. So it's just like the chance of rain. If the chance of rain is 40%, the chance of not rain is 60%. We're just taking 100% and subtracting. Or in this case, and we do it in decimal or fraction form, we take 1 and subtract. So theoretical versus empirical probability. So when we talk about empirical probability, we're talking about letting the computer simulate things, okay? So we talked about above was theoretical probabilities, okay? And so an empirical probability is we actually watch what happens based on observed outcomes. That's us watching what the outcome of the probability experiment is. Okay? And so if I have an unfair coin that lands heads up more often than half the time, but I'm not sure exactly how often, I could flip that coin 100 times and count how often it lands heads up. And if it lands heads up 60 times out of 100, then we're going to estimate the probability is about 60 out of 100, or 0.6, about 60%. Why? Well, we just calculate the number of successes over the total number of trials. That's the fraction, 60 over 100. Number of successes divided by the total number of trials of the experiment. Okay, so theoretical probabilities can be hard to calculate, especially some of the ones we're going to look at. But empirical probabilities are really easy. So look at what this is doing. We're just making a table with one column. It has the title face, and this NPA range 1 to 7 will create the numbers 1, 2, 3, 4, 5, 6. Remember, NPA range always stops one item before the ending number that we put here. All right. And when we execute that, we get what you might think. We get the faces on a die. Okay. So now this is a really cool method. This is the first new method in this book, in this notebook. We're doing die.sample. Okay, so from the faces, right? Basically, we're rolling this die 10 times. Why 10? Well, because that is the sample size and it is put inside the sample, parentheses after the word sample. So we're going to get 10 results, okay? And notice that certain things get rolled more than once. See, right? The ones get rolled more than once. There are 3 ones. There are 2 5s. There are some 4s. They're all kind of strung together except the first one. So this is called sampling with replacement. What does that mean? That means that after you draw it, it can be drawn again. So you draw the 4, but then the 4 goes back in and it's eligible to be drawn again, which happens here, and then it's eligible to be drawn again. So this is the standard default for the sampling function is to sample with replacement. That may be important later. Okay, so then die.histogram. Now remember, the original table is just 1, 2, 3, 4, 5, 6. So when we make this histogram, you'll notice that all the bars are exactly the same height. Right across there, and I can't draw very straight, but if I could, a straight line goes right across there. Why? Well, because as you're aware, each of those probabilities is 1/6. And so we're showing that all the probabilities for the faces showing are the same. We have the same chance of rolling a 4 on the die as we do rolling a 6 or rolling a 2. They're all the same probabilities. That's what this is showing. But now look at this. Now we're changing the bins, and then we're doing die.histogram. Okay, and they're changing the bins. Why? Well, the other one looked a little weird. With these bins they go from 1/2 to 1. That's this bar, right? It starts at 1/2 and goes to 1.5. And then the 1 is there right in the middle. And then from 1.5 to 2.5, and there aren't actually any fractional numbers, right? These are, well, that's fine. So it's just showing that the die faces 1, 2, 3, 4. And this set of bins that we're using makes everything look nice. Okay, we still have just a straight line across the top, which is what we need. Okay, now look at this. So until now, what we've been looking at, right, is we've been looking at a histogram of the original probabilities, the theoretical probabilities. Okay, so what we're going to do right here is we're going to take a sample. So we're going to simulate that we roll the dice 10 times and we're going to see what we get. Okay? So shift enter to run, shift enter to run the cell. And look at this histogram, okay? Notice all of the fours, right? There are 4 fours, and there are a couple of 2s, and the 1, the 3, the 5, and the 6 all got rolled just one time. All right, that's interesting. We can do it again, and we'll get a slightly different picture. See, now here, the 4s seem to have gotten rolled a lot, but so did the 2s, the 3s, and the 5. The 6 didn't get rolled at all, and there were a couple of 1s. Okay, so we got a very different distribution the second time. Why? Well, each time we run this code, it's taking a new sample. Okay. So let me just run it one more time, see what we get. Wow, that's a crazy, ugly looking distribution. All right, so we're going to illustrate what's called the law of large numbers. Why? Well, we're going to take a much bigger sample. Instead of only doing 10 dice rolls, now we're going to do 1,000. And do I have a straight line across the top of my bars like the original distribution, the theoretical distribution? No, it's not quite a straight line, but it's a lot better than when I only draw 10. So the point here that we want to notice is that when the sample gets bigger, the estimate that we get from the empirical probabilities will more closely match the theoretical probabilities. Okay, and then this one is 10,000, and give it just a second. Oh, good, I've already executed it earlier, so it didn't take very long, but it might take yours a while because, I'm sorry, it's not just 10,000, it's 100,000. But the graph of the 100,000 dice rolls, is it a perfect line that could go across here? No, there is that bump, you know, the 1 and the 2 probabilities seem to be a little bit off. But please notice that when the number of dice rolls went up to 100,000, we got a much better estimate from the empirical probabilities of what the theoretical probabilities would actually be, okay? And again, that's the law of large numbers, which you're probably used to, right? We all know that if we flip a coin 4 times, we might get 3 or 4 heads, and even if the coin is fair. But if we flip a coin a couple thousand times, if it's fair, we're going to get a very close to a 50-50 split. And we get closer and closer to that theoretical split of 50-50, the larger the sample size is, right? With a small sample size, like 3 or 4 coin flips, excuse me, let me say 4 and 6, because the only way to get a 50-50 split is if we had an even number. But if I have only 4 or 6 coin flips, I may not get a split that looks very 50-50. But if I have a couple hundred, I am much more likely to get something that looks like the theoretical probability. Okay. So now what we're going to do is we're going to use that scipy.stats that I showed you about right here. And it's a function that's going to work for us, okay? And so we're going to do some complicated probabilities. Now, some of these aren't that complicated, but some of them are, okay? So we're going to do it empirically. We're going to let the computer do it, okay? And so what is this binome? Okay, so this is coin flips, right? There is a success or a failure. And then you tell it the probability of success. So this particular function is doing what we want, right? We need to do coin flips and we need to do 10 trials, okay? So it tells me how many successes. We're looking for 5 successes. So this is the question we're answering, right? What's the probability of getting exactly 5 heads? So number of successes goes first, and the number of trials goes second, and then the probability of success is what goes last. So let me get rid of that marking so you can see, and when you execute it, you find that only about 25% of the time, 24.609, but about 25% of the time we would flip 10 fair coins and get exactly 5 heads. Okay, so yeah, it's likely, it's somewhat likely that we would get 5 heads. Okay, now notice the difference here. This is exactly 5 heads, and this says up to 5 heads. So this is going to be, this is why we're putting in the NPA range, right? Because it's going to count up to 5, right? One less than the number we put as our stopping criteria. And so what is this going to do? The NPA range 6 is going to give us the numbers 0, 1, 2, 3, 4, 5. Okay, so it's going to count if we have 0 heads out of 10, 1, 2, 3, 4, or 5 heads out of 10. So it's going to be everything up to 5 heads. Okay, and then when we run this one, you'll notice that the probability is a little more than 62%, which makes more sense, right? It's pretty likely that if there's a 50-50 chance of flipping a coin and getting a head, that if we did it 10 times, we'd get about 5. And this counts all the possibilities, right? The possibility of getting 0, the possibility of getting 1, the possibility of getting 2, and it adds them all up. Okay. So the next question is, what is the probability that we get at least 1 head? And what the Sam Hill is this doing? Okay, so remember the 11 is one more, the stopping criteria is 11, which is one more than what we'll get. So 10 is going to be the top value. We're going to start at 1 and we're going to go to 10. So we're getting the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We're getting an array with those numbers in them. Why? Well, because the only value in here where we don't get at least 1 heads is if we had 0 going in here. So we're going to get all the other numbers, 1 through 10, from the NPA range, but we're not going to get the 0. Okay, and let me quit drawing on that. And what's the probability of getting at least 1 head? Well, we do this thing 10 times, right? So the probability should be high. Let's take a look. And yeah, you see that it's really close to 1. So this is going to happen about 99.9% of the time. It's almost certain to happen. I'm sorry, I should be underlining this one. My bad. Right? And what's the probability that we get at least 1 head? So these are actually the same cell. Okay, so that just got copied. Sorry about that. And then we're going to take a look at a graph of the distribution. Okay, so notice we're doing NPA range to 11. So 0, 1, 2, 3, all the way up to 10. We're going to get these values that are shown along the x-axis here. And then we're going to get the probability that they happen. Okay, so don't worry too much. We're using this stats.binom.pmf. Again, we have this array called heads that we're calling to go in here, and it's just the numbers 0 through 10, all the integers 0 through 10, inclusive. Okay, we're doing, this means 10 trials, and the probability of success is 0.5. And so when we do that, right, and we create this bar graph, okay, we see the probabilities. And of course, it's, if we're doing 10 coins, we're very likely to see these values in the middle, which are what? The tallest bars are for the 4 and the 5 and the 6. Why? Because if you flip 10 coins, you're very likely to get a 4 out of 10 be heads, 5 out of 10 be heads, or 6 out of 10 be heads. Is it possible to get only 2 heads out of 10? Sure it is. It's a little less than 5%. That looks like maybe 4 or 4.5%. So it's not a real likely thing to happen. It's not as likely as these guys, but it is possible. Same thing. Could I flip a fair coin 10 times and get 8 heads? Sure. Sure. It's possible, but not very likely. So that's what the graph is showing. Okay, now this is what is the probability of getting all 10 10 out of 10 heads. Okay, and notice that we get the opposite of the 99.9%, right? We get a very small percentages, a 0.1%, I guess, if you round that accurately. Okay, so what are we showing? Well, we're showing that it's not very likely to get all 10 heads if we're flipping a fair coin. Okay, and the computer is calculating these for us, so that makes our life easy. So this is empirical probability. Okay, now instead of doing the coin flips, now we're rolling a fair six-sided die 20 times. So that's what's coming in here. This is the binom PMF with 20 trials and a probability of success of 1/6, right? So it's different than the coin flips, okay? And the first question is, what is the probability of exactly 12 fives? 12 out of 20. And please notice that this is a small enough number that the computer switched to scientific notation. So that e to the minus 5 stands for times 10 to the negative fifth. Sorry, I'm trying to draw with my cursor. So we have what, 4 zeros and then the 1, 3, 4, 5. So it turns out this probability is small. So what I'm going to do is I'm going to say that it's very close to 0. I'm not saying this is impossible, but the probability is very, very close to 0. So it's very, 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 very unlikely. Okay, now look at the next thing that we have to do. It says the probability of 12 or more fives. So that's having 12 or 13 or 14 all the way up to 20. So that explains the MPA range going in. The MPA range 12, 21 is going to get the integers between 12 and 20. 20 is going to give us the number of trials. 1/6 is the probability of success. And when we calculate that or estimate that, again, we get something close to 0. All right, so it's a bigger number. It's 1.53 instead of 1.35, right? But it's still times 10 to the negative fifth. So this number is, again, very close to 0. So it's more likely, but not incredibly likely. Why? Well, because it's a fair die. And so rolling 12 is not likely. So rolling even more, like 13, 14, or 15, is even more unlikely. So even when we add all of those probabilities up, it's just not that big. Okay, what's the next question we're looking at? We're looking at the probability of rolling just 2 fives. Remember, we're rolling the die 20 times and keeping track. And what's the probability that 2 of those outcomes happen to be a 5? Well, we're going to have a much higher probability, right? And look, the probability has jumped up to almost 20%, 19.8%. Why? Well, we're only asking for 2 successes out of 20 trials. And the probability of success is 1/6. So if I have 20 times to try to roll it, getting 2 successes happens almost 1 out of 5 times, right? Almost 20% of the time. And what's the next question? 2 or more fives. Okay, so this is the number of successes is 2 or 3 or 4 or 5 or 6, 7, 8, 9, 10, all the way up to 20. Okay, so we have a lot of possibilities, and that's where we're going to use the NPA range from 2 to 21. Why? Remember, it always stops one item before the stopping criteria we put. So the starting criteria is where it starts, and the stopping criteria is one. It ends one before that. Okay, and we're still doing 20 trials, and the probability is still 1/6. And what happens here? That probability is 87%. Okay, well, that kind of makes sense, right? Because we're adding together all of these probabilities, all of the probabilities of the probability of 2 successes plus the probability of 3 successes plus the probability of 4 successes, all the way up to 20. We add all those probabilities together, and it turns out that the probability is about 87%. Okay, so now we're going to take a look at the histogram. And fives, what is this 5 things? This is just an NPA range. What does it get us? It gets us all the integers starting at 0, 0, 1, 2, 3, all the way up to 20. So it just gives us all these categories that we need to create this bar graph. Okay, and I'm going to stop here. And in the next segment, we're going to take up a truly famous statistics example, the lady tasting tea.